Recording. Welcome everyone to the next seminar. So it's very nice to have Cecilia Lunardini, who's coming to us from Arizona State University. So Cecilia is a professor at Arizona State, and she's an expert on neutrinos. And that is what we're going to hear about today, about supernova neutrinos. So thank you very much for taking the time to give us this virtual seminar, and I'll leave it with you. Thank you.
Thank you for inviting me. I really appreciate it. You see the title here, Neutrinos from Supernovae Multi-Messenger Connections. Okay, so what I plan to do is to start with an introduction on core collapse supernovae. I will just call them supernovae for brevity, as multi-messenger emitters. By multi-messenger, I mean the four messengers: photons, neutrinos, gravitational waves, and cosmic rays. And I mostly focus on neutrinos and gravitational waves. And after the introduction, I will cover a bit of my own work, where I took a somewhat unusual perspective of considering supernova neutrinos as sources of other messengers. So I will talk about how neutrinos produce a gravitational memory, and how they can also produce a gamma ray echo. And I will finish with a discussion and conclusions. So let me start with an introduction. So the idea here is multi-messenger. That's the key word. So let's start with the first messenger, photons. Core collapse supernovae are exploding stars. They are the most luminous transients that we know of. And so for this reason, they have been known for a very long time. And in the course of history, they have caused awe and fear in various cultures. So for example, there are records of a supernova, a nearby supernova that occurred in the year 1054 in the Crab Nebula. It was very close, and therefore it was very bright, and it was painted on rocks. It was documented in Chinese records, and apparently, according to a recent paper, it was also represented in Byzantine coins of the time, which is very interesting. Jumping to modern times, the most famous nearby supernova is supernova 1987A, which was the first and only so far supernova to be seen in other messengers other than photons. In particular, there was a neutrino detection. In this case, the supernova was first observed by astronomers who provided basic information on the identity of the star and its location. And using this information, a neutrino experimentalists were able to search archival data and find the neutrino burst from this event. There was no evidence of gravitational waves. In this figure here on the right, you see the neutrino data points. Each data point represents a neutrino interaction in a detector. And you see on the vertical the energies in the range of tens of MeVs, and the duration of the burst, which was about 12 seconds. So let's talk about the physics of core collapse supernovae. A core collapse supernova is the death of a massive star. Stars that are born with about 10 times the mass of the sun. They evolve until they become supergiants, and they go through the advanced stages of nuclear fusion, where medium to heavy elements are fused, including oxygen, silicon, and iron. And iron cannot be fused, being the most tightly bound nucleus, and therefore the production of iron causes a loss of pressure. The nuclear fusion is no longer able to provide the necessary pressure to keep the core of the star in equilibrium, and therefore, through a series of processes, eventually the core of the star, the iron core, implodes, basically, undergoes a free fall, and there is the formation of a very dense object, which is called a proton-neutron star. The proton-neutron star has a very stiff equational state, is practically incompressible, and therefore the matter that falls on it eventually bounces out, producing a shock wave. And this shock wave eventually causes the explosion of the star. Immediately after the collapse, that's where neutrinos become important, because the proton-neutron star loses energy very rapidly through the emission of a neutrino burst of the duration of about 10 seconds. Let's give a little more details on the neutrino emission. And here, the most interesting concept for me is the concept of neutrinosphere. A supernova is the only environment in the universe today where neutrinos are thermalized. The density is sufficiently high to keep them in thermal equilibrium, and therefore they are emitted from a surface. Think about it as some sort of fermionic black body, and the neutrinos have roughly a Fermi-Dirac spectrum with average energies that reflect the temperature in that region of the star, which are in the range of 10 to 20 MeV or so. Now, as I mentioned, neutrino cooling is very efficient because neutrinos are weakly interacting particles. They diffuse out very efficiently. And so they carry away almost the entire gravitational binding energy, which is released in a collapse, which is 3×10⁵ ergs. So it can be easily checked as a back of the envelope calculation by computing the difference in potential energy. The 10 seconds or order of magnitude 10 seconds duration of the burst is explained by the neutrino diffusion time, which again can be estimated from a random walk formula, and just plugging in the relevant numbers, you get indeed about 10 seconds. So you see here in the figure the relevant elements: the proton-neutron star, the neutrinosphere, and then out here is shown the stalled shock. So what's going on here is that for a fraction of a second or so, the shock wave is stalled. It doesn't have sufficient energy to propagate outwards. And one of the most, it's very possible, let's say, that the shock wave is re-energized actually by the neutrinos depositing energy into it. And so eventually the shockwave is re-energized and produces the explosion that astronomers see. The neutrino luminosity, which is depicted here from a numerical simulation, contains a very detailed narrative of the events, of the physics events in the region surrounding the collapsed core. So there is a ramp up of the luminosity here, you see. Then there is a peak, which is almost entirely due to electron neutrinos from electron capture. And then there is a fraction of a second of plateau here, which corresponds to the so-called accretion phase. This is when the shock wave is still stalled inside the star, and the neutrino luminosity is powered by the accretion onto the collapsed core. After the shockwave is launched and starts to propagate outwards, we have the cooling phase, which is the one you see here, this gentle decline over a time scale of a few tenths of seconds, where there is most of the energy loss. And then at the very end, after about, say, 20 to 40 seconds, the neutrinosphere becomes transparent. So there is no longer surface emission, but there is actually volume emission, which typically marks the turn off, or at least a sharp decrease of the neutrino luminosity. A core collapse supernova should produce gravitational waves in the ballpark of about 100 Hertz of frequency. And this should be a robustly visible signal at detectors that are available today, LIGO, Virgo, and CAGRA, for a supernova in our galaxy. You see here in the top plot a typical waveform from a simulation that ran for a few hundreds of milliseconds. And in the bottom plot, you see an intensity plot where you have frequency on the vertical and time on the horizontal. So it tells you the intensity at a given frequency and a given time. And you see that where the intensity is largest, there are two regions. One region is, which is this one marked by A, is the so-called G mode. These are the vibrations of the proton-neutron star. It's as if the proton-neutron star was like a bell, which is being struck and sounds. And so this is a way to explain the G mode. And then there is another region here marked by B, which is a typically lower frequency and starts after about 150 milliseconds. This is due to a phenomenon which is called SASI, or standing accretion shock instability. This is the dynamics of the stalled shock wave. So imagine there is this shock wave which is not moving forward, and it has a large-scale sloshing motion, which produces this gravitational wave emission. Now, in passing, I want to mention that this SASI gravitational wave emission has a neutrino counterpart, which is very interesting. So that's because this large-scale sloshing motion of the shock wave is strong enough to produce some periodic compression and rarefactions of the neutrino sphere, which modulates the intensity of the emission of the neutrinos. And so a neutrino detector would see some quasi-oscillatory modulation of the neutrino the event count in the detector. And so here in this figure, you see in red, there is the neutrino luminosity with the subtraction of a constant component. You see the modulation. And then a very similar plot is the blue one, which is the gravitational waveform. So you see how the two go together. And there is a slight wave shift because the gravitational waves come from a slightly inner region of the star. So I worked on this, and I find it very exciting, but this is not the topic of this seminar. So I wanted to mention it just in passing. Let's talk a little bit about the timing of the different messengers. Neutrinos and gravitational waves are emitted very quickly after the collapse. So you see here in this figure, the red and pink colors are the neutrinos. You see here the time scale, and in blue is the gravitational waveform. And then the black dashed here is the electromagnetic luminosity. And you see it just stays constant. This is the progenitor luminosity. So during the neutrino emission, the star just looks like it looked before the collapse, because it takes time for the shock wave to propagate out to the surface of the star. And when it reaches the surface of the star, it breaks out. That's called the shock breakout, SBO. And that's where the luminosity increases by many, many orders of magnitude. And the star becomes visible by naked eye in the sky if it's nearby. So because of this delay between the neutrinos and gravitational waves and the shock breakout, which is maybe a few hours, then the neutrinos and gravitational waves can be a precious alert of the shock breakout before it happens. So after supernova 1987A, we are still waiting for another multi-messenger detector from the next nearby supernova. The reason the wait is so long is because the reach in distance of neutrinos and gravitational wave detectors is less than 1 megaparsec. So it's a relatively small cosmic region that they are sensitive to. And the rate in this cosmic region is about a few supernovae per century. The rate in the Milky Way is about 1 or 2 supernovae per century. And so that's the reason of the long wait. For more details, you can look at this figure. This figure shows the number of events in Super Kanyokande, which is the blue line, as a function of the distance to the star. Super Kanyokande is a water Cherenkov detector, which is mostly sensitive to supernova neutrinos through this reaction, inverse beta decay, electron antineutrinos interacting with protons, producing neutrons and positrons, and the positrons are easy to detect in the detector. For a supernova in the galactic center, near the galactic center, we expect a few thousands of events. If Betelgeuse become a supernova, we are really lucky. We expect more than 1 million events. But if we go out to, say, M31, which is the nearest galaxy other than our own, then the event rate goes down. The number of events is less than 10. So that shows the sensitivity. And the sensitivity will be better with Hyperkamiokande, which is about 10 times bigger, but still we are limited to maybe a few megaparsecs volume. So this is the end of my introduction, and now I want to talk about supernova neutrinos as sources of other messengers. And my first topic is the gravitational wave memory of supernova neutrinos. So what is the memory? To illustrate that, let's look at this gravitational waveform. And there are two of them plotted here. The bottom one in blue, is a waveform that starts at 0, and then this is for a merger actually, and so you see that there are oscillations, and then when the merger has occurred, the waveform goes back to 0. So the strain goes back to 0. In the top curve in red, it starts similar. The strain starts similarly at 0, but it doesn't go back to 0. So there is a relic effect after the gravitational wave has ended, so to speak. And in this case, we say that the gravitational waveform has a memory. So the memory is this relic effect, which in principle is there forever. And I find this very fascinating. So just to illustrate a bit more, imagine having a configuration of test masses and having the gravitational wave pass through your screen, orthogonally to the screen. And without memory, this configuration would get distorted, but it would eventually recover its original shape. But if there is memory, it would be distorted and retain a certain degree of distortion at the end. So this is what memory is. And it's actually a well-known prediction of general relativity. So it's a very cool effect, which is predicted by GR. It's a permanent distortion of the local space-time metric, which is caused by gravitationally unbound systems. So in order to have memory, you need to have two things. You need to have a system that emits either mass or radiation, and the emission has to be anisotropic. And the signature of the memory is a permanent change in the distance between two free-falling masses. And that means that there would be a signal at gravitational wave interferometers. Now, the memory is one of those general relativity predictions that hasn't been observed yet. It's a small effect. And in order to have a chance to observe it, we need to have a very powerful emitter with some degree of anisotropy. And the supernova is just perfect for that. It emits an enormous amount of energy, most of which in neutrinos. And the neutrino emission is predicted to have some anisotropy at the level of 1% or slightly less. Also, I want to point out that because the neutrino emission timescale is of the order of 10 seconds, if you convert that into a frequency, we are talking about sub-Hertz scale, which is attractive for the next generation of decihertz detectors that are designed to explore that region of, say, 0.1 Hertz or so. So, how to compute the strain with memory? This is something that has been done in the literature, so I will just refer to that for it. Here, I just want to give an idea of how to go about it. Of course, you need to set up a suitable frame of reference where you have your extended source emitting neutrinos in our case, and you have the observer at a certain distance r. And the starting point is Einstein's equation, not surprisingly. And of course, one has to do some steps. And the goal here is to calculate the tensor H, which describes the change in separation of free falling masses through this equation, where L is the separation vector between these two masses. So the result here is given for the longitudinal polarization HXX. And you see here it goes like G over R, and there are two integrals. One of them is over time, and one of them is contains the neutrino luminosity differential in solid angle multiplied by a geometric angular factor, okay, which describes it's something that describes basically the geometry of the observer with respect to the emitter. And a more convenient way to cast this result is the one in the box down here, where we have this, for brevity, I'm calling this h of t, and there is the integral over time, and the angular dependence has been lumped into a single integral into a dimensionless quantity, which is called the anisotropy parameter alpha of t. So this 1 over L is to make it dimensionless. And so you see here the final practical form, where you have an integral over time of the product of the neutrino luminosity times the anisotropy parameter. So this is the master formula that I'm going to use in the next few slides. So let's talk a little more about the anisotropy. There is prediction for the anisotropy from numerical simulations. You see here a result from these authors. And the trend here is that anisotropy starts at 0 and develops over a few hundreds of milliseconds due to SASI, and also due to convection near the collapsed core. So you see here it has a complicated time dependence, and its size is roughly about 1%. And this is a two-dimensional core collapse simulation. So here is some references just for those that are interested, just pointing out that the first papers on this date back to 1974. So there is a long history. Now, in my work with my former student and postdoc, Moina Kmukupadia and Carlos Cardona, we studied the memory from a phenomenological point of view, and we wanted to build a phenomenological model for it, for the reason that numerical predictions exist, but they only extend to maybe a few milliseconds, and they are time consuming. So a phenomenological model is useful for applications and phenomenological studies, detector sensitivity studies, and more. So to build our model, we started by taking toy models for the two main ingredients, one of them being the neutrino luminosity, which we modeled as a constant plus a declining exponential, where the parameters lambda, beta, and chi are free parameters. They can be adjusted. And we took a toy form for alpha of t as a constant plus a number of Gaussians. And again, there are a number of parameters that can be adjusted. And if you take these two analytical forms and you plug them into the master formula that I have shown before, you get this analytical result, which I'm not expecting you to read, but just keep in mind that there is a closed analytical form for it, which is practical to use. And this is in time domain, h of t, and we also have an analytical form for h tilde of f, which is its Fourier transform. So here you see various parameters defined as functions of the original parameters of the two ingredient functions. So this is our phenomenological model, and we tested it against numerical results to see how well it performs. So we took our toy luminosity, which is the dash curve, and we showed that it's a reasonable match to numerical simulations. And at the bottom plot, we have alpha of t, numerical versus our toy model. You'll see that there is a reasonable agreement. We don't worry about these fast spikes in the numerical simulations, because our goal is to reproduce the sub-Hertz a part of the signal, which is the bulk of the memory signal. So these spikes would contribute only to high frequency that are not particularly relevant here. So if we take these two dashed lines and we put them in the master formula, we get this blue dashed line here for h of t. And you see how it compares with the numerical result, which is plotted here as a solid line. And it's a decent agreement. We get an even better agreement in using this dot dashed line, which is what you get if you take our analytical h of t and fit it at that level to the numerical results. So you see that the agreement is pretty good. So having tested our model, then we used it to produce a number of case studies, which I'm going to show here. You don't have to look at all the details. Let me just say this is for a supernova at 10 kiloparsecs, which is a typical galactic distance. And the model which is closest to the numerical simulation you have seen in the previous slide is the solid line, where we have assumed that is this blue solid line, where we assume that the anisotropy is non-zero only in the accretion phase, so only in the first, say, half a second, and we assume that after that it's zero. We don't know because numerical simulations don't extend that far. But as a conservative assumption, we assumed it's zero during the cooling phase. And that causes this fast reaching of the plateau value, which is about 10 to the minus 22. We get an even simpler form if we take a simpler shape for the anisotropy parameter, which is just one Gaussian curve. We get this simple rise. And then we change the parameters. We considered a slightly more optimistic model with accretion only anisotropy, giving a larger result. And then in the bottom, we have two models where we consider that the anisotropy could be non-zero throughout the neutrino burst, so for more than 10 seconds. And in that case, the rise of the memory is slower, as you can see here, and it plateaus to a larger value. So you can see this dashed line here as an example. So using these models, these case studies, we did a detectability study where in this figure I show this HC of f, which is the modulus of the Fourier transform of h of t multiplied by twice the frequency. It's kind of a standard quantity to use. And you see how our various case studies are shown here from the most conservative to the most optimistic. And you see here this form, there is this asymptotic behavior at low frequencies, and then the decline above 1 Hertz. And you see how these signals compare to the sensitivity of one proposed detector, which is the SIGO. The SIGO is one of the proposed deci-Hertz detectors. And the sensitivity curve is this one. So you see that for 10 kiloparsecs distance, even the most conservative memory model would lead to a detected signal, which is quite encouraging. Now, I'm aware of the fact that the SIGO is proposed, but we don't know if and in what configuration it will be built. So here is an overview of the detectability for other detectors. In this case, we have taken our most conservative model and plotted the signal for several distances from 0.1 kpc to 1 megaparsec. And you see the sensitivity curves of various detectors. Here is the SIGO, and we also plot BBO, MAGIS, Einstein telescope, and more. And so what we see here is that a detector like BBO, for example, will be sensitive to supernovae as far as about 1 megaparsec, which is the reach of neutrino detectors. And if we have the most ideal detector, which is this one, Ultima de SIGO, this corresponds to some sort of best case scenario for the SIGO, the best that can be achieved with the SIGO technology. This would go down by a few order of magnitude and would be sensitive to the memory up to tens or even hundreds of megaparsecs, which is more than the sensitivity of a megaton scale neutrino detector. So this is quite interesting in my view. So if we have a supernova, say, in our galaxy, then there would be a robust detection of neutrinos with high statistics. And if we have a large decihertz detector, we would have the memory detection as well. If we have these two detections, then we can compare the two signals. And the neutrino detectors would give us the luminosity, which is one of the ingredients of the memory effect. So by comparing the observed memory and the detected neutrino signal, we can maybe extract information on the anisotropy, this alpha of t function that you have seen. And this is a way to probe the fluid dynamics in the accretion phase. The memory comparison with the neutrino detection would also probe invisible cooling channels, because the memory is sensitive to every form of energy emitted, not only neutrinos, but also light scalars, sterile neutrinos, and more. In principle, comparing the two data sets would give us a hint of the existence of some extra cooling channels that we just don't see, if we assume something for the anisotropy. So there is a bit of model dependence there. Finally, because of the potential large distance of sensitivity, the detection of the memory can be used to enhance the performance of neutrino detectors. And this is something that we have studied. I will just mention that very briefly. We have a follow-up paper with Moinak Mukhopadhyay and Zidu Lin on using the memory as a time trigger for neutrino detectors. So this figure shows the idea. The idea is that we imagine having an ideal scenario in which you have a large neutrino detector like Hyper-Kamiokande, for example, and a very sensitive decihertz detector like the SIGO or BBO, or even better. In that case, you could run the gravitational wave detector for a few years, maybe 5 years, for example, or 10 years, and have several memory observations. And for each memory observation, we have the arrival time, this T1, T2, T3, and so on. And so we know that there should be neutrinos arriving at Earth in, say, an interval of 10 seconds or so following the detection of the memory. And so this is how the time trigger works. We just look for neutrinos in those time slices immediately following the memory detection. And we will, this sample will be of supernovae that are very distant. So for many of them, there will be no neutrino detected, but maybe for some of them, there will be maybe one neutrino detected. And so we can collect all these detected neutrinos, and because of the time trigger, these neutrinos will be practically background free. So this is a way to reduce the background greatly. The background is mostly due to atmospheric neutrinos in the detector. So I'm jumping directly to the results of this project, and it's shown in this figure. So this figure shows that it shows the number of neutrinos, time trigger neutrinos, for a detector which we call the SIGO Plus, providing the time trigger. So the SIGO Plus is a detector that would be 10 times more sensitive than the SIGO. And we paired it with a megaton water Cherenkov detector operating for 30 years. So this is very ambitious, I admit that. And what's plotted here is the number of neutrinos from supernovae that are time triggered up to a distance d in megaparsecs. So the meaning of this figure is that this LIGO Plus detector would be able to time trigger up to a distance of about maybe 40 megaparsecs. And using this time trigger, we can maybe expect something between 10 and say 30 or so neutrino events, practically background free. You see how low the background is at this point. The background increases if you take time triggers up to larger distances, but for say 50 megaparsecs or so, it's not a problem at all. Okay, let me now switch to another topic, which is the gamma ray echo of supernova neutrinos. This is a fun project that I really enjoy working on. And it started in a kind of funny way. It started from my frustration over neutrino detectors being too small. So even a megaton water Cherenkov detector is too small for my taste, because it's still limited to, say, a few megaparsecs distance of sensitivity. And so I thought, how can we come up with a bigger detector? And so I thought, if the main detection channel is inverse beta decay, the target here is just hydrogen, and the universe is full of hydrogen. So let's leverage that. And so I thought we could, in principle, look for positron production in the envelope of the star. So the star is collapsing, but the envelope remains intact for several hours. And so the envelope can be used as a mega detector. And the positrons will propagate in the stellar envelope, and they would lose energy pretty quickly for the most part. And so they would eventually annihilate at rest. So the signature here is the plus and minus annihilating into 2 photons of the characteristic energy of 511 keV, which is a characteristic positron signature in gamma rays. So this idea was interesting, and I was excited about it. And then I quickly realized that this was not new. It was actually proposed in 1975, and there is, you see here, 2 seminal works on it. And there is also a third work by Liu and Chen from 2007, where the nuclear physics is worked out in detail. In particular, the positron propagation is detailed there. So still, I wanted to really understand this better. And so with some collaborators, we studied what we call the gamma ray echo supernova neutrinos. So these gamma ray photons would be time delayed compared to the neutrinos. And that's illustrated in this figure. So the neutrinos come to us directly from the core of the star. So they follow this direct path in red. But when the envelope of the star is illuminated in 511 keV gamma rays, the gamma rays that come from a point on the star away from the line of sight will be time delayed, okay, because they follow a longer optical path. And so according to the definitions here in this figure, the time delay would be R over C times 1 minus cosine of theta, where R is the radius of the star. And also, I want to clarify that pretty much the photons that we can observe would come from a very thin shell near the stellar surface, because photons that are produced too deep inside would be absorbed. So we are talking about a thin shell of width about the mean free path of the gamma rays. And so it's possible to estimate the flux of gamma rays that we would receive here at Earth as a function of time for a star of radius r and distance d. And you see here it goes like 1 over d squared. There is the inverse beta decay cross section. There is the Compton cross section, which describes this photon mean free path. And there is an integral of the neutrino luminosity over the stellar surface, so over the various time delayed paths. Okay, so here is a sketch of what you can expect. So these two curves are not on scale, but just for illustration, just look at their shape. The dashed line shows the neutrino burst of the duration of about 10 seconds. You see it starts to drop after, say, 20 seconds or so. And as the neutrino signal drops, the echo comes up. So the echo rises, and it lasts, in this case, about 1,000 seconds for a stellar radius of 10 to the 13.5 centimeters and a distance to the star of 1 kiloparsec. This is the gamma ray flux over here that we can expect. And 1,000 seconds is about 20 minutes. So it's much longer than the neutrino burst. And these dark circles illustrate what an observer would see corresponding to the various times. So at very early times, we would only get the gamma rays that come pretty much from the line of sight. So this tiny illuminated dot in the center of the sphere. But then as the time passes, we receive gamma rays from a larger and larger region. And until eventually the echo dissipates because the neutrino flux, the parent neutrino flux has dissipated. So this is the meaning of this figure. And here is the reference. These are three ASU students, Loeffler, Hurley, Farag, and my colleague Frank Timmis. Our paper has just been accepted in APJ. And here is the main result of our paper. So we computed the light curve of these gamma rays for different stellar radii. So you can see here, this is for, I believe, a star at 1 kiloparsec distance. And just for simplicity, look at the vertical axis on the left. This is the gamma ray flux, and as a function of time, and look at the solid curves. So for larger radii, we have a longer echo of lower flux. And the total number of produced photons is the same in all cases, but for larger stars, the echo is spread over longer times. And so important also here to see is the comparison with the galactic background of 511 keV photons, which we found in the literature. And so it depends on the direction in the sky. So that's why I have this shaded region. But you see here that the galactic background can obscure the signal for certain parameters. And so we had to worry about this background. And so here is a more detailed plot that answers the question of detectability. So in order for this echo to be detectable, we need a large enough detector, first of all. And so we computed this NS, which is the number of detected photons, which is shown here in this figure as these horizontal lines for an ambitious hypothetical detector of 10 to the 3 centimeters effective area, which is very ambitious, but not totally unrealistic. And so you can see here that the distance of sensitivity is basically of the order of a kiloparsec. So for 0.6 kiloparsec, we predict three photons observed. And so this is the first condition. You need to have a large enough effective area to have at least a few photons detected. And the other criterion for observability is, of course, that the signal should be at least comparable to the galactic background. And this is what these shaded areas are. So basically, at a glance, the region which is covered by the shaded areas is where background can be problematic. To give more details, here we have distance on one axis and stellar radius on the other axis, and we plotted each individual supernova candidate in our immediate surroundings. So you see the famous ones, you see Betelgeuse, Antares, Rigel, and a few others. These are all supergiants that are supernova candidates, and they are marked in different markers depending on the signal to background ratio. So the orange axis are the stars where the signal would be overwhelmed by the background, because the background depends on where the star exactly is relative to the galactic center. So closer to the galactic center, the galactic background is stronger. And so these are the unfortunate stars. Like Antares, for example, is one of the unfortunate ones. But Betelgeuse is promising. Rigel is very promising. And several others are promising in that respect. So if we are lucky and nature gives us a near-Earth supernova, we could detect the echo. And just returning to the question of having a large enough effective area, we found that in the literature there are a couple of proposals. One is Amigo, the other one is Gecko, for gamma ray detectors that would have achieved this large effective area. And also I forgot to say that in order to estimate the background, we assumed that we can restrict the background to a cone of angle 3 degrees around the position of the supernova. So what can we learn if we observe the gamma ray echo? I find it interesting that the gamma ray echo is a way to test the neutrino emission away from the line of sight. So these are neutrinos that wouldn't reach us in neutrino detectors, but we would learn about them indirectly from observing their byproduct gamma rays. Also, we can consider the envelope of the star as acting as a near detector. So we can have super Kamiokande or hyper Kamiokande as the far detector, and the envelope of the star as the near detector. And comparing the two would give information on things that may happen between the stellar surface and Earth, like, for example, neutrino decay or some exotic neutrino oscillations. Also, the echo is a complementary way to measure the stellar radius, because its duration depends on the stellar radius. And also it's a way to test for the composition of the stellar envelope, because this echo is expected for hydrogen envelopes. If the star has an envelope which is mostly helium or carbon or so, then the echo would be very much suppressed. So to finish, what does the future hold? So the next galactic supernova, whenever that is, will be a multi-messenger event, very exciting. There will be a high precision, real-time detection of neutrinos and gravitational waves at 100 Hertz frequency. And this will be powered by an array of detectors that are planned or existing or planned to be built, like Hyper Kamiokande, Juno, Dune, LIGO, Virgo, and Kagra. And of course, there's an immense potential to learn physics. Neutrinos and gravitational waves will provide alert to the astronomy community, and they will also deliver very detailed information on the physics near the core of the collapsed star. And also we can use this neutrino burst from a supernova to test neutrino properties and maybe do some tests of gravity or new physics. So lots and lots of things to do. This is the most likely scenario. But it's possible that maybe in a more distant future, or if we are really lucky and have a supernova really close to Earth, we could observe phenomena that are signatures of neutrinos without actually detecting the neutrinos, which I find quite intriguing. So, for example, if we have a good decihertz detector for a supernova at several megaparsecs, we may not see the neutrinos, but we may actually see the memory from the neutrino burst, which could be used as an alert or it could be used to test, say, the dynamics near the collapsed core, as I mentioned earlier on. If we have a near-Earth supernova like Betelgeuse or Rigel, then we could observe the gamma ray echo if a good high effective area detector exists. And this echo would be mostly due to gamma rays, to neutrinos produced that propagate away from the line of sight. So this would be neutrinos that wouldn't end up in a neutrino detector, but we would learn about them indirectly from the gamma ray echo. And this is also a way to test for anisotropy, in the sense that we could test for emission away from the line of sight versus emission on the line of sight. And also, it's in contrast with the memory, this is a way to test for near surface physics. So it's something that depends on what happens near the surface of the star. So I will stop here. Of course, this is all very exciting. We are waiting for the next supernova in our galaxy or nearby. So thank you.
Thank you very much. Yeah, do we have questions? Roland, you want to go ahead first?
Oh, sorry, was it me?
Yeah.
That was fascinating. Thank you very much. So I had two dumb questions or dumb ideas. So the first question is, I mean, there've been many supernovae over the history of the Milky Way. So is there in any way a cumulative effect on the of the gravitational wave memory from like that there are many supernovae?
I thought about it. And I would have to think more. So I was thinking, maybe let's see if we had the same idea. So I was thinking, suppose you have an interferometer that runs for, say, 30 many years, like a century, and then it would, or maybe even 30 years, it would pick up many faint memory signals, and then they would accumulate and create some sort of like diffuse background. But I'm not sure, because I'm not sure if this would be observable, because it would this would be changes. It would be changes in the metric that would maybe average out, because they would have all sorts of different orientations. But I would have to think some more. I'm not sure I can give a valid answer to that question. But it sounds like you were thinking more about historical signals. And considering that it's an effect of, it's a tiny effect, maybe like the strain is 10 to the minus 22 or so, I'm not sure we have something that can provide historical records.
Sure, thanks. Well, if there are, I mean, I've got another question if there's nobody else asking.
Yeah, sure, go ahead. Well, I'll let you have your second one. Yeah.
Well, the other dumb question I had was, so you said that to see the 511 echo of the neutrinos interacting in the star, basically you need to produce the positrons within the photon mean free path of the surface of the star.
Right.
So what about, how does the column of that material compare to just the column of material you have in your detector for the neutrinos? What if the neutrinos just interact directly in the detector? Is that completely negligible?
I'm not sure I understand the question.
So if you have the inverse beta decay, the neutrinos actually propagate all the way out, and then they produce the positron in your detector.
Right.
Can you just ignore that? Is it just trivially tiny in comparison to the? I assume what you've got to do is you've got to compare the column of material of protons in the detector to the column
Yeah.
that the neutrinos have to propagate out
Yes.
within the mean free path.
Okay, so I think I understand now. So I guess the general question is how can we think of the envelope of a star as a detector? Is it how similar is that to say Super Kamiokande? A detector like Super Kamiokande is thin to the neutrinos. So the neutrinos would just pass through it, and a tiny fraction of them would leave a signal. And the gamma rays, well, in Super Kamiokande, the positrons would be detected before they lose energy and annihilate. So Super Kamiokande detects the Cherenkov light from the positron, not the gamma rays from the positron annihilation. The envelope of the star is like a huge detector, which is so big that that we would have positron annihilation, and then the signal would be the reduced gamma rays. So in that respect, is different. I'm not sure I'm actually answering the question, because I'm not sure I understood it well. But it's I'm not sure I can compare the two directly. So yeah, I may have to think about this some more.
No problem. Thanks.
So can I ask again about these gamma rays? So you were comparing the gamma ray signal against the diffuse galactic flux as your main background, but I mean, if we're thinking seriously about like Betelgeuse or something, this is like a spectacularly bright event. This will be. Are you sure there's no other source of 511 keV gamma rays just from the shockwave? Just the fact that you're seeing it something that is so bright that any small detail you're going to pick up basically if you point a gamma ray telescope at it.
Yeah, when I was working on this project, I was kind of worried about it, but then after consulting one of my collaborators, who is a kind of stellar evolution expert, we concluded that there wouldn't be other sources of gamma rays from the star, significant sources of gamma rays, because what could you have? The shock wave is still deep inside the star. So we're talking, these gamma rays would be emitted way before the shock breakout. So the envelope of the star doesn't know that the core has collapsed. So there is no effect yet of the shock wave. And deeper inside the star, you could have things like heavy nuclei undergoing de-excitation, or beta processes producing gamma rays. But those typically would occur deeper inside the star where those elements live. This would be the inner part of the star, and this would be more than a mean free path away from the surface. So those gamma rays would be produced, but they wouldn't propagate out. So yeah, that was, we worried about it, and that was our conclusion, that the galactic flux is probably our main enemy.
And I guess for these like really nearby ones, are these nearby enough that you like a decent size issue detector would be seeing the neutrinos during the silicon burning phase and the pre supernova neutrinos? So do you
yes,
appreciable gamma ray signal from that phase, or is it you need the main burst to see the gamma rays?
We really need the main burst. There should be a detection of the pre-supernova neutrinos from, say, silicon burning, but that neutrino flux is very weak, so it would be enough to detect it directly, say with Juno, for example, but its gamma ray byproducts wouldn't be intense enough to be detected. So yeah, only the burst would produce a significant gamma ray output.
Roland?
Well, if nobody else has got any other questions, I was going to ask, with respect to with the idea of the memory effect with the supernovae. So there must be some connection between the size of the kick that the neutron stars typically get and the anisotropy and the size of the memory. Is that right?
Broadly speaking, I would say so. We didn't look into that. I'm not sure it's a direct connection though. So we still don't know. This is something that I'm not familiar with. I think I understand your reasoning. If there is an anisotropy in the neutrino emission, maybe there is a net momentum that would produce the kick. So I agree with the reasoning. I'm not sure it's a direct connection in the sense that there may be many other things that would somehow dilute the connection between the two. But in principle, I agree with the idea. We didn't look into that connection.
Okay, I just wondered whether that because you had the slide with detectability and you had an upper bound. I just wondered what the origin of the upper bound is.
Yes, and also just to finish the answer to your question, the anisotropy is not something, it's something that can change over time. So you may have anisotropy for, say, half a second, and then it may reverse because of the turbulence and SAS and so on. So it may not have a net macroscopic effect. But the bound, let's look at it. That one is really simple. It's what you get if you maximize all the ingredients. So basically, if you take the master formula and you just maximize L nu, maximize alpha, it's just phenomenological bound. We took alpha to be, say, 10 to the minus 2 maximum, and then you take it out as a constant, and then you get the integral over time of L of nu, which is 3 10 to the 53 ergs, and those numbers give that upper bound. So it's really nothing profound.
Okay, thank you very much.
Yeah. Sure.
Anyone else burning to ask a question? I don't see any hands up. So yeah, maybe we thank Cecilia again. Thank you very much for taking your time out